Okay, for the sake of time, what I want you guys to do is I want you to take a minute and pause this video and fill in the three little tables for the first three rows of this large table about even functions. These are three of your parent functions. You're going to need a calculator for the cosine, one, because you're going to have strange decimals for it, but take a minute, pause, and fill in this large table here about even functions, and then I'll fill in the paragraph at the bottom for you. Okay, hopefully you paused it and you filled in the large table, and hopefully what you notice is that all three of these graphs are symmetric across the y-axis. What that means as far as their tables of values is that when you have one x value and a y value in the table, then the point with the opposite x value but the same y value is also in that table. So negative 2, 2 is in the table of absolute value, well, so is positive 2, 2. If the numbers in your cosine table don't look like mine, that's probably because you might have been in degrees instead of in radians. And so you can simply redo that, or you can fill it in using the numbers that I've got here, because we do pretty much all of our trig work in radians this year. So how the tables were all alike is what I just said, is that when you have opposite x values in the table, they have the same y value attached to them. And all of the symmetry is similar. That's all identical. Exactly. They are all symmetric across the y-axis. So this is the easiest type of symmetry to see graphically. You can graph these functions and just spot the symmetry across the y-axis. But we don't do a lot of it graphically, we do most of it algebraically. So what the algebraic definition says is that for every x value that's in the domain of the function, the negative x has to be there too. So kind of what I pointed out in the table, that if positive 2 is in the domain, so is negative 2. And the y value when you get when you plug in the negative x, or the opposite x, is equal to the y value that you got for the original x. So if the point AB is on the graph, then so is the point negative AB. And that makes them symmetric with respect to the y-axis. So then the next table introduces you to some of the odd functions that you've seen before. They're parent functions as well. And I want you to, once again, take a minute. This time make sure your calculator's in radian mode, because you're going to be doing sine. And pause it and fill in this table. Okay, so hopefully you took a quick couple of minutes and filled in the three tables, and hopefully you were able to verbalize the graphical symmetry. It's a little harder to explain. One of the most common ways people want to say it is they want to say it's symmetric across the x and the y axis, and you just need to make sure you specify that it's got to be reflected across both axes in order to see the symmetry. But if you imagine taking this part of any one of your graphs, and you've either got to reflect it twice, so the first time you would reflect it across, the y-axis or something, and it would flip over here, and then if you took it and flipped it across the x-axis, it would reflect right over there. So it would reflect over on top of the other half of the graph, but you'd have to reflect it twice. The way that I visualize it, and some people are pretty good at doing it too, is I visualize sticking a little brad right here at the origin, and I take this section over here in quadrant 1 and I imagine rotating it around the origin 180 degrees. So if I took this and I swung it around 180 degrees, it would rotate right over on top of that quadrant. And the same thing goes for this one. If I took quadrant 1, which was right there, that's that branch of the graph, stuck a little brad right here in the origin, then I would take that and swing it around 180 degrees and it would swing right over on top of that branch of the graph. And so that's what makes these graphs symmetric about the origin or around the origin. Okay, so these tables are all alike because when you have opposite x values, so the opposite x values, this time around, they produced opposite y values. So, for example, sine of 2, and don't forget I was in radian mode, was 0.909, but sine of negative 2 was negative 0.909. So opposite x values produce opposite y values. And so how they're different from the even functions is basically already been stated, because even functions, opposite x values produce the same y values. And in odd functions, opposite x values produce opposite y values. The symmetry of even and odd functions is not the same, because this type of symmetry either has to use rotation to generate it, or two reflections to generate it, not just over the y-axis, but the y and the x. So once again, we're not going to spend a lot of time just looking at them graphically. It's just to help you visualize and introduce you to these two kinds of symmetry. But the algebraic definition says, once again, that for every x that's in the domain, so if 2 is in the domain, then the negative x also has to be in the domain. So negative 2 also has to be in the domain. And when you plug negative x into the equation, the answer that you get is the opposite of the original f of x value. So if I plugged in positive 2 and I got this, then when I plug in negative 2, so that's the f of negative x down here, then I'm going to produce the opposite of the original y value. So if the point AB is on the graph, then so is the point negative A, negative B. And they're symmetric with respect to the origin. Now there's lots of other kinds of symmetry, but there's only two others that we're even going to talk about in pre-cal. Most of your other symmetry is all geometry. Okay, we're not in geometry anymore. So the other two kinds of symmetry, if you're symmetric across the x-axis, then that means that you're going to have an object that maybe looks like that. That would be symmetric across the x-axis, but that means that it's not a function, because each x value is going to generate two y values, so that means that it fails the vertical line test. So because pre-cal is predominantly the study of functions, we're not going to be proving this algebraically. And then if your relation or your function can be divided in half in any way, then it's got a line of symmetry. It may not be algebraic, it may not be an axis. So for example, all of your conics from Algebra 2, if you had a circle way up here in quadrant 1, that's got a ton of different kinds of symmetry, but we can't prove it algebraically. Once again, it fails the vertical line test. It's not a function. Okay, so now I want you to graph these functions. It says in your calculator, if you don't have your own calculator, then you've got, you could at least do A and B, because those are just transformations of a parent function, and then you could hold off and we'll look at C together. Or you can get online, and there's all kinds of free online graphing calculators, so you could graph that one really quickly. So I don't want detailed graphs, just quick sketches of what these look like. So you're going to pause again for just a minute, and you're going to quickly sketch these 3 graphs. Okay, so like I said, even if you don't have a calculator and couldn't do C, you should have a quick sketch of A and B, because A was just your parent quadratic, moved down to -5 for the vertex, so just a parabola. And then B was just your parent cubic function, shifted down 1, so now your y-intercept is right there at -1. And then even if you had a graphing calculator, C is a little bit trickier to sketch, because you need to make sure that you don't have your window zoomed out too far, because otherwise you're going to miss this tiny little peak and valley that are right here in the graph. So you may need to resketch that really quick, or you can hold off on that. And you're supposed to be making a conjecture about whether they're even, odd, or neither. So I'm hoping that you can look at A and you can see that it's still symmetric right across the y-axis, so we already know that this one's going to be even. A lot of people make the conjecture that B is odd. I'm actually going to show you algebraically how we know that it's not. And then C is going to end up being odd, but once again, I'm going to prove it algebraically. And for the sake of space, I can't write that small. I'm not going to try and cram it into the table at the bottom of this. I'm simply going to create a blank page and do each of these. So we're going to start with x squared minus 5. So f of x is x squared minus 5. And I'm going to prove algebraically that it's even, just like I thought it looked graphically. So according to the definition of even, when you plug -x into the equation, you're going to get the same answer as when regular x was plugged into the equation. So this right here, that's the original equation. That's f of x. So all I have to do to prove that this function is even is I have to prove that when I plug -x into the equation, I get the same thing as the original. So that's what we do. We plug -x into the equation. So I'm going to take my equation, I'm going to replace x with -x, so that's this part right there, and then it gets squared in the equation, and then a -5. And then I simplify. And when you take that -x and you square it, what does it become? Yeah, it becomes positive. Squaring anything makes it become positive. So -x squared becomes just x squared. And then there's the -5. And sure enough, that is the same as the original equation. So you just proved that it's an even function. Okay? The next one was x cubed minus 3. Or x cubed minus 1, I'm sorry. And so a lot of people, like I said, they make the conjecture that they think it's odd. So let's see if we can prove that. If odd, then when you plug -x into the equation, you should get the opposite of the original equation. So what that means is that I'm going to plug -x into my equation. And there's two ways I can go about doing it. I can do that and then I can simplify it, and I can see if it's the opposite of the original equation. Some people have trouble visualizing why it may or may not be the opposite of the original equation, so I could also actually figure out what the opposite is and see if the two things equal each other. So if I did f of negative x, so I'm going to plug negative x into the equation. So I replace x with negative x, and it gets cubed, and then a minus 1. And this time, though, I'm cubing that negative. Well, cubing a negative leaves it negative. So I don't need the parentheses anymore. It's just going to be negative x cubed minus 1. And like I said, some people can look at that and go, that's not the opposite of the original equation, but some people do get mixed up because they see a negative out in front of it and they think, oh yeah, it is the opposite of the original equation. So if that's the case, what you would do is you would take all of f of x and you would put a negative out in front of it and simplify. So I'm going to take all of f of x. The original f of x was x cubed minus 1, and I'm going to put a negative out in front of it. And then I would simplify it. And when I simplify it, this negative would distribute through. And so I would see that if it was really the opposite of the original equation, all of the signs in the equation would have changed. So these two things aren't equal to each other. This is what I got when I did f of negative x. And it's not equal to what I got when I did the opposite of f of x. So I just proved that it's not odd. Now, that doesn't mean it doesn't have any kind of symmetry. It just doesn't have algebraic symmetry. It is still symmetric about its y-intercept, but that's complicated. And we don't prove it algebraically. We're only trying to prove these two kinds of symmetry algebraically. We already know that this function's not even. We know it graphically because we could tell it didn't reflect across the y-axis. We also know it algebraically because when we got our answer for f of negative x, that answer also was not equal to the original equation. So when we plugged negative x into the equation, we didn't get the original equation back, and we didn't get the opposite of the original equation. So it's not even a not odd, and so we call it neither. Doesn't mean no symmetry. It just means doesn't have the two kinds we prove algebraically. And then the final one that we're going to prove was f of x is 5x cubed minus x. So I'm just going to go with the method or the route that we use for pretty much all equations unless y isn't isolated. Okay, and we'll deal with those in class because we're doing these notes flipped so that we can practice in class. So what we're going to do is to test for symmetry, we simply plug negative x in. So that's what I'm going to do. I'm going to plug negative x into my equation. And I'm going to simplify and see what I get. So I plug negative x in right there, and that one's being cubed, and then I plug negative x in right there. And then I simplify. So when I simplify this first part right here, that negative's being cubed, so it's going to stay negative. And then it's being multiplied by 5. So that first term is going to be negative 5x cubed. And then when I simplify the second part of the equation, I'm subtracting a negative x, which is going to make it become plus x. And so then you have to ask yourself, okay, well, what did I get? Did I get the original f of x back? No, we didn't, because everything in the equation had a sign change. And so what that means is that we got the opposite of the original f of x back. Everything in our original f of x had a sign change done to it, so that's the opposite of f of x, and so we've just proven algebraically that our function is odd. And remember that this was the graph that looked like this, had a tiny little peak and a tiny little valley. And so if I did that rotation or reflection twice, if I put a little brad right here at the origin and I took this part of it and I swung it around 180, it would fold over right on top of the other part of it. So it is odd. It is symmetric about the origin. So we're going to practice this in class. So don't worry about it too much. We wanted to do these notes so that we could help you practice, because it takes practice to do this algebraically. So don't worry about it. We'll help you.